Hello students, today we will discuss some numerical problems in basic electronics. Let us calculate the barrier potential for silicon junction at 100 degrees Celsius and 0 degrees Celsius if its value at 25 degrees Celsius is 0.7 volts. So we know the barrier potential for silicon junction at room temperature is given, which is 0.7 volts. We are asked to find out barrier potential at two different temperatures, and you know the barrier potential is dependent upon temperature. And what is the equation? Yes, the equation for barrier potential, the change in barrier potential with temperature is given by it decreases with temperature. So hence a minus sign is the into 0.002 into difference in temperature, or you can put it as T2 minus T1. So now substituting, we have a potential at a temperature 25 degrees Celsius is known, which is given by 0.7 volts, and we are asked to find it at 100 degrees Celsius. So what would be the difference in temperature? It would be 100 minus 25. So we have 0.002 into 100 minus 25. So that comes as 75, or that is equal to minus 0.15. Okay, and that is how we evaluate. So what will be the potential at here? That is only the difference. So what will be the potential? The potential could be written as, or the barrier potential could be written as VB at 100 degrees Celsius can be written as how much? Will be equal to VB at 25 degrees Celsius. Okay, 25 degrees Celsius. Then plus the difference. So what is that? The difference is obtained as minus 0.15 volt. Okay, and we know the value of VB at 25 degrees Celsius, it is 0.7. So it will be 0.7 minus 0.15, which is equal to 0.55 volt. Okay, so that is how we evaluate the barrier potential at a given temperature. So this is evident, that is the difference in VB is same as the barrier potential at 100 degrees Celsius minus barrier potential at 25 degrees Celsius equal to delta VB, and delta VB is obtained as minus 0.15, and which could be substitute and find out. So similarly you can do it for 0 degrees Celsius also. So you can try out that question or that part of the question. And another question could be like the same question could be repeated for a germanium junction also, and let us take the same temperature itself, 100 degrees Celsius and 0 degrees Celsius. So how do you evaluate? The same procedure can be done. Only thing is that the room temperature barrier potential is not given. So you have to know that the room temperature barrier potential for silicon is 0.7 volts, and for germanium it is 0.3 volt. Okay, so then you can evaluate the change in potential. This would be 0.15 itself, minus 0.15 itself, and while you evaluate VB at 100 degrees Celsius, it would be VB at barrier potential at room temperature, which is 25 degrees Celsius. So it is not mentioned in the question, but you have to take it as such. Okay, plus the difference. So the difference is given as 0.15 volt. Okay, so only difference is that the potential at room temperature is different from that for a silicon. So here it would be 0.3 as we have mentioned, 0.3 minus 0.15. So it would be 0.15 volt. Okay, so that is the barrier potential depends upon, though the difference in temperature are the same, it depends upon the kind of junction also. So here also you can do it for 0 degrees Celsius as well. Okay, and the next question is, in an unfiltered half-wave rectifier circuit with input supply voltage of 240 volt and 50 hertz given across a transformer of turns ratio 20:1, find the DC output voltage across a resistor of 1 kilo ohm. So hope you remember the circuit for a half-wave rectifier. So let us draw the circuit first. So you have a input supply given to a transformer with turns ratios given. Okay, so that is a secondary coil, and for a half-wave you know it has only one diode in the circuit and is connected in series with the resistance RL. This is a circuit. So what are the given quantity? The input supply voltage is given 240 volts and their frequency AC signal. So frequency of AC signal is also given, which is 50 hertz, and turns ratio is given, that is NP is to NS is what you mean by turns ratio, that is given. And what is that? It is equal to 20:1, which means there are 20 turns in primary while 1 turn in secondary, or 20:1 ratio also can be considered. And RL is given 1 kilo ohm, kilo means 1000, so it is 1000 ohm, and diode is given. We are asked to find out what is the DC output voltage across the resistor. Okay, so how do you do it? We know we need to, first of all, we must get what is the secondary voltage. How do you get the secondary voltage? From the turns ratio you can obtain. So secondary voltage is given by the primary voltage into NS by NP. What is the primary voltage? It is the supply voltage. So you can write it in substitute over here. So it becomes 240 into NS is 1 divided by NP is 20. So it comes as 12 volt as secondary voltage. And the maximum or peak value of secondary voltage is given by √2 times of the value Vs. So substituting that, you will get it as 16.97 volt. Okay, and for a half-wave rectifier, DC output voltage is calculated as Vd is equal to Vm by pi. So substituting for Vm, you will get 16.97 divided by, or approximately 17 divided by pi, which is 5.41 volt. I think you can substitute 16.97 itself. Okay, so that is the DC output voltage. So knowing the DC output voltage, you can evaluate further parameters also. So the question could be like, you could evaluate what is the load current. So the load current, you have to infer that it is IDC. And how do you get IDC? The current is obtained by corresponding voltage. So IDC means corresponding voltage is VDC divided by load resistance. So how much it would be? So we can calculate as 5.41 divided by RL. RL is 1000 ohm. So which means 1.41 milliampere ആയിരിക്കും കിട്ടുന്നത്. And you can also evaluate from the VM also, maximum secondary voltage. So because VDC, you know Vm by pi, so you can evaluate in that way also, or in terms of current also, because Vm by RL will give corresponding current. Vm in the corresponding current or IR. So in that way also you can evaluate. Either of the equation could be used. So maximum current is evident. It is given by Vm by RL. So Im means adinde corresponding voltage, that is Vm, divided by resistance to be considered. So there is only one resistance in the circuit, so it is RL. Okay, So if you are considering the resistance of diode also, then you will have to substitute it as RL plus small r. Okay. So if the resistance of the diode is given, you have to substitute it as, because it is a series connection, the diode resistance as well as the load resistance will mount to the total resistance in the circuit. And another factor is you can also evaluate knowing Vm, peak inverse voltage can be evaluated. That is, for a half it is equal to Vm. And also you can find out what is a ripple frequency. And what is ripple frequency? Ripples are the, we know in the output of half-wave rectifier we are getting as ripples, not as a steady one, it appearing as ripples. So what is the frequency of these ripples in the output? So if you check the frequencies given by, if you consider a particular time, how many peaks are involved, contained in it, how many peaks are there? Only one. Okay. So similarly, let us consider the same interval for output also, and let's check how many peaks are contained in it. How many peaks? It also has only one peak. So which means the frequency of ripples in the output is same as the frequency of input. Okay. So given the input frequency, it is already given 50 Hertz. So the ripple frequency will be the same, 50 Hertz itself. So you can evaluate all these parameters. So the next question is, the same question can be done for a full wave center tapped rectifier. Full wave, here it should be wave, full wave center tapped circuit with input supply voltage of 240 volt, 50 Hertz given across a transformer turns ratio to is 20:1 and diodes of resistance 10 ohm each. So the diode resistance are given here. Find the DC output voltage across a resistance of 1 kilo. So if you remember the circuit again, you have a input supply, and from which it is connected to the transformer whose turns ratio is given as 20:1, which means for 20 turns in secondary you have only 20 turns in the primary, you have one coil in the secondary, and the full wave center tap has a connection from the center terminal also. So this is like, you can draw like this, RL and one more diode, so two diodes in total, so forming this. Okay, so when you consider closed circuit, you will be considering only up to here. Okay, so which means only half portion of the secondary has to be considered. That is the difference from the bridge rectifier or half rectifier. So first, initially you need to find out what is Vs, and half of Vs will be taken. So what is Vs? Again, we can use transformer ratio, that is primary voltage into Ns by Np. So it is the same, 240 into 1 by 20, which is equal to 12 volt. But here the peak value has to be considered only across half of the secondary. So the peak Vm is given by root 2 into Vs by 2. So substituting 2 by 2, 6 into root 2, it become 8.48 volt. Now our aim is to find out what is the DC output voltage. So the DC output voltage is given by, for a full wave rectifier, it is given by 2 times Vm by pi. So we know Vm, so substituting that, you will again get 5.404 volt. Okay, and similarly we can calculate other parameters also, you can try out yourself. So we can calculate what is a load current, and it is given by corresponding voltage divided by resistance. Load current ayukonde load resistance matram consider cheytha madi. So VDC by RL, or you know VDC is 2 Vm by pi, so we can substitute and find out. Similarly, we can find out what is the maximum current, which is given by Im. So here you can see that the diode resistance is given, and one load resistance is also there in a one closed loop. So you can substitute Vm divided by total resistance is given by diode resistance plus load resistance. So then you can evaluate. And for a full wave center tapped rectifier, peak inverse voltage is given by 2 times Vm. So substituting Vm, you can calculate what is the peak inverse voltage. And ripple frequency is about 2 times input frequency. Why? Because if you consider a particular time, you can say only one peak is involved. If you consider the same time, you can see since D1 will be forward biased in the first positive cycle, and during the negative cycle D2 will be forward biased in the same direction, and hence you will get two or a continuous ripples. So here you can see for the same time instant there are two peaks involved. So what would be the frequency? It would be 2 times the input frequency. So it would become 2 into 50, which is 100 Hertz. So all these could be asked. So let us extend the problem to the bridge full wave rectifier also. So here you can see the same question is given. So you have evaluated the secondary voltage, and the difference is that here we will be considering the entire secondary voltage. So Vm is root 2 times Vs. So we can evaluate that, and DC output voltage is obtained as 2 times Vm by pi, or it is, sorry, here there is a mistake, it is 16.97. So it would come up as 33.94 watt. Okay, divided by pi is also divided by 3.9. So let us evaluate that. So it would be 2 into 16.97 divided by 3.1. So you can see 10.8 is the answer. So this would be almost like 10.8 watt. Okay. So that is the difference. So the same question can be applied to a half wave or full wave, or a bridge full wave or center tap full wave. So based on that, your understanding, the answers will be different. Okay. So here also you can calculate what is the load current, which is corresponding voltage, that is VDC. IDC is given by VDC divided by RL. And for bridge rectifier, so let me come back to the, or let me draw here itself. So here for a bridge rectifier, you have primary coil, then secondary coil, then it is connected to what? Yeah, it starts from here, an arrow mark to the right, that is D1. Similarly, you have arrow mark in the lower side also, D2, and they are joined, and here it will close the loop. Okay, so this is a bridge rectifier, and here you have a resistance RL, which is connected across the point, these 2 points. Okay, so here you can see, for if you consider a closed loop, it would always contain 2 diodes. That is, if it is positive cycle, this one and this one will be forward bias. So the circuit always contain one diode plus resistance plus another diode, and it will end back to the end side. Okay, so every time it consists of 2 diodes and 1 resistance in parallel. So here the maximum current will be evaluated as Vm by 2RV plus RL. That is the difference from half wave and full wave rectifier. And the peak inverse voltage is also shared among the 2 diodes, so it becomes Vm. and ripple frequency is same as that of the center tap Fullway rectifier. So here also you can see this corresponds to this position. So negative cycle RL across the direction same aricum. So you'll get a peak, positive peak in the ripple in the output. So you can see two ripples are involved, and hence the input frequency will be 2 times the input frequency. Sorry, ripple frequency will be 2 times the input frequency. Okay. So those are the 3 kinds of questions, and one question is from transistor. So let us check that. A transistor is connected in common emitter configuration to a supply of 10 volt. The voltage drop across RL or RC of 1 kilo ohm is 2 volt. If alpha is equal to 0.98, calculate the collector emitter voltage VC and base current IB. So this is the common emitter configuration where emitter is common to the input as well as the output. So what is the input current? It is IB, and output current is IC. Okay, so we are asked to find out what is the voltage across collector and emitter. VC has to be found out. So how do you get VC? Yeah, this is from the supply VCC. So will you get the total VCC to be dropped across the collector and emitter? No, because it has to travel along a resistance path RL. So what happens, there would be with respect to the current, that is collector current is the output current or the current in that circuit. So based on that, a voltage drop will happen. So VCC minus this voltage drop will give the voltage across collector and emitter. So that is given. So the voltage drop across the resistance is given by current into resistance, IC into RC, and it is given as 2 volt. So we have 2 volt here. So from which you can calculate what is the collector current. So collector current will be given by the voltage divided by resistance. 2 divided by RC is 1000. 1 kilo ohm means 1000. So it is 2 milliampere. Now what is to be found out? We need to find what is voltage between collector and emitter. So how do you get it? The supply voltage minus voltage drop across the load resistance. So VCC is given, how much it is? 10 volt. Okay, 10 volt minus IC into RC, voltage drop across RC is given 2. So you'll get it as 10 volt as VC. So that is our one answer. And next question is, we have to find out base current. So the base current is given by, or the current amplification in the case of common emitter configuration is given by output current. What is output current? Collector current divided by input current. Input current is IB. So from which you can write what is base current. It is equal to IC by beta. But whether the beta is given in the question? No. Another factor, alpha, is given. So alpha is the current amplification factor when base is common to input and output circuit. Okay. So in that case, you can write alpha as output current is collector divided by input is emitter. IC by IE. Now let us relate alpha with beta. For that, let us consider beta equation, that is IC by IB. So we know the current starts from emitter, isn't it? So the emitter current will be somewhat recombined in the base, and it's constitute IB as the base current, and the remaining will be reaching the collector current. So you can write IB as the emitter current minus collector current. Okay, now what we do? Yeah, we need to get alpha as IC by IE. So we divide throughout by IE. So in the numerator it become IC by IE divided by 1 minus IC by IE. Okay, and we know what is IC by IE, which is alpha. So substituting, we get beta as alpha divided by 1 minus alpha. So if you know the current amplification factor in common base configuration, that is alpha, we can obtain what is beta, that is current amplification factor in the common emitter configuration, and hence we can evaluate base current. So let us directly substitute beta as alpha divided by 1 minus alpha. So it become 1 minus 0.98 into the numerator divided by 0.98. So it become 0.04 milliampere. So these are the kind of questions you can expect from the basic electronics. Okay, thank you.